Refraction of light. Refraction is defined as the change in direction of light when it passes from one transparent medium into another of different optical density. The incident ray, the refracted ray, and the normal all lie in the same plane. The velocity of light. It varies according to the density of the medium through which it travels. The more dense the medium, the slower the light passes through it. Suppose this is dense medium, so here the light will be slower, the wave runs at slower velocity. When a beam of light strikes the interface separating a less dense medium, this is a less dense, this is a more dense, a less dense from a denser one, obliquely, the edge of the beam which arrives first, the A part of the beam, it is retarded on entering the denser medium. The opposite side of the beam, the B part, is meanwhile continuing its original velocity. The beam is thus deviated as indicated in this figure and being bent toward the normal. This is bent toward the normal. The normal is a line perpendicular to the interface at the point of refraction, and so the beam bent toward normal as it enters the denser medium. Now a comparison of the velocity of light in vacuum and in another medium. Vacuum and another medium, it gives a measure of the optical density of that medium. The measurement is called the absolute refractive index N of that medium. Absolute refractive index is equal to velocity of light in vacuum and divided by velocity of light in the medium. The absolute refractive index can be determined by using a refractometer. The refractive index of the medium compared with air is the velocity of light in air divided by velocity of light in a medium. Now we will give certain examples of the refractive index. The refractive index of air is 1 when it is divided by it is compared with vacuum, or when it is compared with air. The watt 1.33, refractive index of cornea 1.37, crystalline lens 1.386 to 1.406, crown glass 1.52, flint glass 1.6, diamond 2.5. On entering the optically dense medium, from a less dense medium like from air to glass, light is deviated towards the normal, is shown in this figure. The incident ray makes an angle I, which is the angle of incidence with normal, and the angle between the refracted ray and the normal is called the angle of refraction R. These angles are governed by the refractive indices of the media involved according to Snell's law. Snell's law states that the incident ray, the refracted ray, and the normal all lie in the same plane, and that the angle of incidence and refraction are related to the refractive index N of the media concerned by the equation N medium N1 to medium N2 is equal to sine angle of incidence divided by sine angle of refraction, where the first medium is a vacuum. N is the absolute refractive index and in air n is the refractive index. When the first medium is vacuum, then n is the absolute refractive index, and when it is in air, then it is called refractive index. If however the interface is between two denser media of different optical densities, for example water and glass, then value of n for that interface may be calculated by n is equal to n glass divided by n water. So generally, on passing from one medium 1 to medium 2, the index of refraction is equal to n2 divided by n1. n2 divided by n1. Light passing obliquely through a plate of glass. So light passing through a plate of glass is deviated laterally. An emerging ray is parallel to the incident ray. Thus the direction of the light is unchanged, but it is laterally displaced. It should be remembered that some reflection also occurs at every interface, even though in this case most of the incident light passes onward by refraction. For example, a lens or window with a refractive index of 1.5 in air, it reflects 4% of the light from the interior surface and transmits the remaining 96% to the posterior surface. A further 4% of this is reflected, so the lens only transmits 92.16% of the normal incident light. Now this figure illustrates the use of a sheet of glass as an image splitter. For example, the teaching mirror of the indirect or thermoscope. Now as you can see, most of the light is refracted across the glass to the examiner's eye. However, a small portion is reflected at the interior surface of the glass and enables an observer to see the same view as examiner. Now refraction of light at a curved interface. Light passing across a curved interface between two media N1 and N2 of different refractive indices, it obeys Snell's law. So this is a convex spherical curved surface. It causes parallel light to converge to a focus if N2 is greater than N1. Here N2 is greater than N1, so light will converge to if N2 is greater than N1, or the light will be diverged if N2 is less than N1. For example, from glass to air, suppose here is glass and here is air, so the light will be diverged, and this is air, and here is cornea, so the light will be converged if light comes from air to cornea. Now the refracting power or vergence power of a curved surface, it will be given by N2 minus N1 divided by R. N2 minus N1 divided by R. What is R? R is the radius of curvature of the surface in meters according to the sign convention, and the surface power is measured in diopters. Surface power is positive for converging surface and negative for diverging surface. Positive for converging, negative for diverging. The interior surface of cornea is an example of curved refracting surface and example of such a refracting surface. Its power accounts for most of the refracting power of the eye. Now real and apparent depth. Objects situated in an optically dense medium. They appear displaced when viewed from a less dense medium. This is due to refraction of the emerging rays, which now appear to come from a point I, the virtual image of object O. Objects in water seem less deep than they really are. For example, one's toes in the bath, they appear less deep than they really are. This principle applies also to surgical instruments in the anterior chamber of the eye. Now, total internal reflection. Now, the rays emerging from a denser medium such as glass to a rarer medium such as air, it suffer a variety of fates depending on the angle at which they strike the interface. At different angles, their fate will be different. So this is ray A. It strikes at 90 degrees to the interface and is undeviated. Ray B. It emerges after refraction. As the rays meet the interface more obliquely, like the C and D, a stage is reached where the refracted ray, for example, the ray C, runs parallel with the interface. The angle C is called the critical angle. This is critical angle. Rays striking more obliquely, it will fail to emerge from the denser medium and they are reflected back into it as from a mirror. It will act like a mirror then. This is called total internal reflection. The critical angle is determined by the refractive indices of the media involved. For example, here it is glass and air. It can be calculated using Snell's law. The critical angle for the tear film air interface, suppose this is tear film and there is air. Tear film air interface is 48.5 degree, and for crown glass air interface, this is crown glass and this is air, then it is 41 degree. Total internal reflections also occurs at surfaces within the eye, notably the cornea and air interface. This is the cornea and this is air interface, and prevents visualization of parts of the eye. For example, the angle here is the angle of the interior chamber, and peripheral retina is also not visualized. This problem is overcome by applying a contact lens. This is contact lens made of material with a higher refractive index than the eye, and filling the space between the contact lens and the surface of the cornea with saline. So it will destroy the cornea air refracting surface and allow visualization of the anterior chamber angle. This is known as gonioscopy, and also the peripheral retina by a 3-mirror lens. Total internal reflection is used in optical instruments. Prisms make excellent reflectors by total internal reflection. Fiber optic cables, which are used to deliver light from a remote source to the point where it is required, also depend on total internal reflections. Examples include the surgical intraocular light source, the transmission of laser light from the laser tube to the delivery system of the laser slit lamp. Fiber optic cables consist of many fine transparent fibers bound together in a flexible external protective sheet. Light enters the end. Here you can see light enters the end of each fiber and is reflected onward by total internal reflection until it emerges from the far end without significant loss of radiant energy. Bending the optical fiber does not impair its efficacy. Dispersion of light. So far, this discussion of refraction has overlooked the fact that white light is composed of various wavelengths. In fact, the refractive index of any medium differs slightly for light of different wavelength. Light of shorter wavelength is deviated more. This is light of shorter wavelength. It is deviated more than light of longer wavelengths. Blue light is deviated more than red. The refractive index of a material is normally taken to mean that for the yellow sodium flame, the angle formed between the red and blue light around the yellow, it indicates the dispersive power of the medium, which we will discuss in chromatic aberration. This is not related to the refractive index of the material. The total internal reflection and dispersion occur in the rainbow. When sunlight enters a raindrop, this is a raindrop. Sunlight is dispersed into its constituent spectral colors. Here you can see. Under certain circumstances, the angle of incidence is such that total internal reflection then occurs within the drop. The dispersed light finally emerges, each wavelength or color making a different angle with the horizontal. To see the rainbow, the observer must look away from the sun. The observer receives only a narrow pencil of rays from each drop, only one color. The whole rainbow is the result of rays received from a bank of drops at increasing angle to the observer eye. Violet, the color making the smallest angle to the horizon, is received from the lower drops, while red, making the greatest angle with the horizon, is received from the highest drops. Thus, the red is on the outside of the primary rainbow. This is primary rainbow. The secondary rainbow is formed by rays that have twice undergone total internal reflection. This is secondary rainbow. Within the raindrops, it has undergone twice a total internal reflection, and the colors are seen in the reverse order. Violet is on the outside of the bow and the red on the inner side.